Let's take a look at the previous example we've done for the Edgeworth box. And this is basically what we've done in the previous video, where we had the utility functions for both Alex and Billy. And we drew the Edgeworth box by combining both of their utility functions. So we end up getting this final utility, this final Edgeworth box for both Alex and Billy. And in this example here, we want to figure out mathematically their demand functions and how much they are willing to forego. Like, we want to figure out the math behind achieving this point right here, which is basically their utility maximization point. So let's first explore what Alex and Billy's budget constraints are. And in this case, their budget constraints is basically equal to their endowment points, because this is how much they can each consume. So we know that Alex can consume 5 of good X and 2 of good Y, and Billy can consume 1 of good X and 3 of good Y. So we know that the equation for the budget constraint is basically equal to their income times the price of good X multiplied by the number of good X plus the price of good Y multiplied by the number of good Y. And this gives you their budget constraint. And since we know that their budget constraint is equal to their endowment, we're able to substitute some of these variables for numbers. So let's start by finding the budget constraint for Alex. So Alex's income, or his budget constraint, is equal to the price of good X times the number of good X he consumed, which in this case we know is 5, plus the price of good Y times the number of good Ys which he can consume, which is 2 in this case. And let's do the same thing for Billy. We know that the income for Billy, or their budget constraint, is 1 of good X and 3 of good Y. So perfect. That's the first step, which is finding out what their budget constraints are. The second step we want to do is we want to basically figure out what their demand functions are. And the way we do that is we want to use the Cobb-Douglas shortcut to take their utility functions and find out what the demand functions for good X and good Y are. Now let's review the Cobb-Douglas real quick. So we know that the Cobb-Douglas shortcut is basically, if we want to find good X, then it's basically term A over A plus B multiplied by the income over the price of X. And if we want to find good B, demand function for B for a specific person, find the demand function for Y, you take term B over B plus A and multiply that by I over PY. We'll take a look at what that looks like in an example. So since we're given the utility function for Alex, we know that the utility function for Alex is basically equal to X to the power of 1, 2, 1/2 times Y to the power of 1/2. And if we try to find good X for Alex, the demand function for good X for Alex, we know that this is equal to A over A plus B multiplied by I over PX. And that is basically, let's identify what the variables are. So A in this case is 1/2, this exponent right here. And B is basically the exponent of the Y term. So let's sub those in. So we know that XA is equal to 1/2 over 1/2 plus 1/2 times the income over the price of X. So we get XA is equal to income over 2 times the price of X. So this is one of the demand functions for Alex for good X. Now we want to do the same thing for good Y. So let's do the same thing for good Y. Let's make a divider here. So we know that good Y for Alex is equal to the B term over B plus A multiplied by the income times the price of Y. And Y term for Alex, we have the exponents. And basically that is equal to I over 2 py. So this is the second demand function we have for Alex. So these are the very important terms that we're going to need for the future calculation. Now let's fast forward and do the same exact thing for Billy. So we figured out what the budget constraint for Billy is. Let's figure out what term XB for Billy is equal to. And we know that X is basically term A over, let's quickly write their utility function from up here. So we know that Billy is X to the power of 1/3, Y to the power of 2/3. And let's solve for Billy's demand function, first demand function. And we get 1/3 over 1/3 multiplied by, plus 2/3 multiplied by I over the price of X. So we get the demand curve for X, which is 1/3 plus, I over 3px. And let's do Y real quick as well. Let's extend this line right here. And we know that term Y is basically B over B plus A multiplied by the income over the price of Y. And that's equal to 2/3 over 2/3 plus 1/3. Multiply that by income over the price of Y. And you get the second demand function equaling 2 over 3 I over py. So now we figured out the demand functions for Billy as well. The next step that we want to do is we want to sub in the budget constraint for both Alex and Billy into each of these terms that we've calculated the demand functions, which is XA, XB, YA, and YB. So let's start with Alex again. So we know that their budget constraint is income is equal to 5px plus 2y. If we sub that into the first equation, which is XA, let's go ahead and sub that in real quick. So we know that XA is equal to income over 2px. So we want to sub Alex's income into this equation. And basically, it's going to be 5px plus 2py. So we're going to take XA equals to 5 px plus 2py over 2px. And then after solving for x, we get 5 over 2 plus py over px. Now let's do the same thing for y for Alex. And we know that condition is I over 2py. So let's sub in those again. Let's sub in that budget constraint into Alex's y function. And we end up getting 5px plus 2py over 2py, and that is equal to 5px over py plus 1. So now we have these two conditions for Alex. And now we want to do the same thing for Billy. So you know that Billy, the x term for Billy is equal to I over 3px. And we want to sub in Billy's budget constraint now, which we figured out also right here, to be px plus 3py. Over 3px, and we get 1/3 plus py over px. And let's do the y term for Billy, which we figured out to be 2/3 times I over py. And if we sub in that, 2 times px plus 3 py over 3 py, we get 5px we get 2 over 3 px over py plus 2. And now we have all four terms where we subbed in the budget constraint for both Alex and Billy into the demand function. Now we want to look at the market clearing condition to basically figure out how many of each unit they're willing to trade in order to achieve utility maximization. So we call this the market clearing condition. For the demand functions. So we know from their endowment that the total number of goods available for good X is 6 units, since it's 5 units for Alex plus 1 unit for Billy. So we're going to use that market condition because we know we can't consume more than 6 of good X in the economy. So we know that the good X for Alex plus good X for Billy will always equal 6, or 6 is basically the maximum number of units in good X in the economy. And we already know what the demand functions for good X for Billy and good X for Alex are, because we figured them out right here. And what we're going to do is we're going to add both of these together to basically figure out what the price is. So let's denote, since we have the same variables here, let's denote that as just being P for price. So now we have one variable to solve for. So we'll do, what we're going to do is we're going to take 5 over 2 plus Py over Px plus, which is basically XA, and we're going to take 1/3 plus Py over Px, and we're going to set that equal to 6 units. So let's remember how we said we're going to donate Py over Px equal to P. Let's do that real quick. So 5 over 2 plus P plus 1/3 plus P equals to 6. And now we get P is equal to 19 over 12. Now what we want to do is we want to sub P into the basically XA and XB functions right here in order to see how many units of Alex is willing to trade and how many units of X Billy is willing to trade. Let's do that real quick. So we're going to sub P into XA and XB demand functions. So we have XA is equal to 5 over 2 times plus 19 over 12. And that's basically equal to 30 plus 19 over 12, which is equal to 49 over 12. Let's do the same thing for B. For Billy, 1/3 times 19 over 12 is equal to 4 plus 19 over 12, which is equal to 23 over 12. And if we add both of these together, we are going to get 72 over 12, which is equal to 6. Since it satisfies the market condition where we can only consume 6 units of both good X for Alex and Billy combined, then this holds true. These are the number of units Alex is willing to trade and the number of units Billy is willing to trade from good X. Now, since we already said that, since we mentioned that we denoted Py over Px as being P, so that means that Px over Py is equal to 1 over P. So what we can do now is we can use the same formulas, but now for Y right here, and basically sub in 12 over 19. Since P is equal to 19 over 12, then we know that 1 over P is equal to 12 over 19. And we can sub this term into basically these functions to figure out the Y quantity for each. And at the end, we're going to check to make sure that it satisfies the market condition, because we know in total, both of them can only consume 5 units of good Y. So let's go ahead and do that. So again, just subbing in numbers. So we get good Y for Alex as being 49 over 19. Let's do the same thing for Billy real quick. Again, just subbing in 12 over 19 for the Px over Py variable. and we get 46 over 19 units for Billy. So this is how much each of them are willing to trade for good Y. And if we add both of these together, we get the market clearing condition, or it satisfies because 49 plus 46 over 19 is equal to 5 units.